Good afternoon, everyone. So today we are going to start talking about stochastic processes more generally and formally. But we will begin our consideration thinking about the probability densities in probability space. So a convention we are going to follow throughout is, imagine you have some space in which you are studying the system. It could be physical space, and you are watching a particle undergo stochastic motion, right? Or it could be some space of different chemical concentrations, and you're observing how the system fluctuates, how its concentrations are fluctuating. Okay. So let's say I have some coordinates x2, x1, x2, x3, and so on, okay, n dimensions. And this is the state of the system. In dynamical systems, this would be the phase space, and this would be the state of the system. And now, because it's stochastic, it is doing some kind of motion. Okay. So this trajectory we will label with capital X. Okay. And the coordinates in state space we will label as the vector x, okay, which is the collection x1, x2, and so on. Here are the different coordinates. And what this just means is that this will have the value okay. So just to distinguish in your mind, so when you think of capital X, think of trajectory, okay, of the system, of a particular realization of the stochastic process, right? Because what we are thinking about now is the evolution of some variable, right, or some set of variables in time. Okay, so this is a particular trajectory, but if you repeat your quote-unquote experiment, you will get some different trajectory, right, because the underlying process is stochastic. So when you see capital X, think of trajectory, right? And if you see small x, you think of the probability space, right, and the coordinates in that space. So with this in mind now, if I start thinking about the probability densities, right? So for example, the simplest one will be given some stochastic process, and I can have trajectories doing all kinds of things depending on where they start, right? At any given time, I might want to ask, what is the probability of finding the system at this particular point in the probability space, right? So that would be the probability density. Okay, so the simplest one is just the probability of finding the particle at some position x, right? Again, it's a vector because it's n-dimensional space at time t, right? And this we've already encountered it in Einstein's derivation. This is something you would have seen before. Okay. So this just gives me the distribution of the system in space, right, depending on how I started. And this, of course, depends on how you initialized whatever you're looking at, right? So if you're thinking about Brownian particles, are you saying that they all began at the origin, or were they initially randomly distributed? So that will affect this quantity. So you can already see that this does not give you all the information. Okay. Even if you forget about that and just think about a trajectory, right? This PDF, okay, does not have any information about trajectory. It's just telling you that at some time, where are all the particles, right? From this, I cannot construct any particular trajectory, right? Because it's not going to tell me that if I started at this position, how will I evolve, or what is the probability of doing a certain kind of evolution as opposed to some other. Right? All that information is not here. Okay, so this is in fact quite minimal. What we really need for a full description of the stochastic process, right, is probability of trajectories in this space. Right? That means if I start at some position initially, then what is the probability of going to another position, then another, and then I can do this for any possible choice I would like to find out, right? So what I would really need Right? So this has no trajectory information. Right? So if I want a full knowledge, right? Specifically, this is what I'm going to say holds for separable stochastic processes, but that's the kind of system we are going to be looking at throughout. Okay, so the full knowledge of the stochastic process, right, would require me to know something like this. Okay, so what this means is that I really want to, I should be able to say what is the probability of undergoing some arbitrary trajectory. Right? And the way I've written it is that T2 is less than T1. So this is further in the past, this is more recent. Okay, that's the convention we'll follow. So what it's saying is that I should know the probability of, say, let's say I want to start at some point, right, xn tn, that's the original starting point. And then I can choose any path and say what is the probability of my particle executing this particular motion, right, at any times and at any positions. Then you should be able to tell me the probability. Okay. Now from this, we will see that we will be able to, of course, construct this by summing over all trajectories that bring me to some place. This is what we did, right, in Einstein's derivation. So we will see that later. But so I really need this. If I have this, I can say anything about the system, right, and construct anything. This is, of course, quite complicated because it's completely general. Right? It's not saying anything about how I will go from one to the other. Right? It's expecting you to know this. Okay, so this is just like saying what is the probability of any particular trajectory. Okay, and what we would like to do when we are thinking about stochastic processes is ultimately we want to understand how the system is evolving in time. Right? This is the way we would come to it in terms of prediction, right? Or if you think of it in terms of dynamical systems or as a differential equation, ordinary differential equation, what we're usually doing is saying I know the past and I want to predict the future. Okay, so just with that in mind, I can just rewrite this as a convention to say that that what we want to do is predict the evolution, okay, which would be, I mean, this is now just a rewriting for the sake of making things clear. Okay, so what we are typically interested in doing is predicting the future, which means that I know because I have observed, right, or because I am setting it, the past, and I want to know what will be the probability of having various futures. Okay, so in the way I've written it, the y's and the tau's are the past which I have measured or which I know, and the t's and x's is what is going to happen in the future. Again, time ordered so that tau 2 is before tau 1 and so on, and t2 is before t1. Okay. So it's like saying I have observed a particular set, a particular trajectory, and I know this information. So then I want to know what's going to happen in the future with what probability. Okay. So this is different from this, right? This is a joint PDF, which is just like saying what is the probability of any particular trajectory. I'm not saying that I know anything in particular, right? But here I'm saying I do know some part of the trajectory in the past, and I don't know the future, and that's what I want to find the probability for. So this is the joint, it's a joint PDF, right? Or if you want to think of it, it's like just a PDF of this trajectory. If I mark some points, right, xn, n plus 1 and so on up to x1, This is the probability of that particular trajectory. But here I am saying, okay, I know some part of it, either because I've observed it or because that's what I'm interested in, right? I'm only interested in understanding trajectories which did something, and now I want to know what's going to happen. So this is of course the situation, for example, if you want to predict the climate, right? I have observations, right? Or I'm going to impose certain constraints, and then I want to know what's going to happen after that. Okay. Now notice that at this point we have not made any assumption about history dependence, right? In fact, we are allowing it to be general, because we are saying that it's not enough for me to just know this past or the current state, right? I'm saying that maybe the entire history will affect what is going to happen in the future. Okay, so this is the general situation. We have not made any assumptions about history dependence yet. But what we would like to do first is just to see mathematically, right, how can I relate a conditional distribution of this type to the probability of trajectories. Okay, so remember I said this is the basic information we need if we want to understand everything. If I know this, I should be able to derive all other quantities, right, including this instantaneous distribution at any time. And so I should also be able to get this. Okay. So how will I get this from the probability of trajectories? Right, so you have to remember your basic probability. So the way to think about it is, can I write this in terms of this? Right, so what would that be? So this is the probability of some trajectory. This should be equal to the probability of, right, a trajectory given some part of it into the probability of realizing that part, right? So then if I flip it around, this should be equal to the probability of the trajectory divided by the probability of experiencing what I am assuming, okay, what I have taken for granted. So this is the usual conditional probability business. Right? So this is equal to divide by the probability of having experienced the past that I am assuming to hold here. Okay. So these are just some preliminary notions which you already know. I'm just recalling it in the present context. Okay. Okay, so now what we'll do is we start making our way towards what are Markov processes, right, where we are going to make some simplifications and say certain things about the system we are considering. So far what we've done is completely general. Okay, any process with any kind of complicated dependence on the past can be thought of this way. So just to take an extreme example, right, if you think of human history or something like this, right? So something that happens today, if a war breaks out, it doesn't only depend on the state of the world right now, right? It depended on stuff that happened a long time ago. So most general processes one can think of this way, which has non-local dependence on time. On the other hand, most physics problems, right, if you increase the number of variables sufficiently, can be modeled as being dependent only on the present state, right? At least certainly on the systems we are going to consider in this course. And those are Markov systems. Right? So for example, right, so you just think about the pendulum, right? The pendulum is swinging. So if I only think about the position x as the variable and I try to determine the future position, right, I'll find that it's not enough to just know x, right? Because what is the probability of being at a certain position? It's not enough to know, okay, that it's just not the position, right? It's also the velocity, right? But if I don't know about the velocity and I try to model this, I will realize that I will feel that it has some history dependence. I will have to know x now and x at least one future time. Okay. And I can develop some empirical model in this way. So if Newton had tried to model planetary motion or motion of a ball or something, anything with inertia, just knowing the current position would not be enough. You would have to know at least one previous position, and then he could maybe develop some kind of empirical model. Right? But what he realized is, no, it's not, I really need the acceleration. Right? So I need time derivatives. So if you increase the space to position and velocity, then you can have a dynamical system description that only depends on the current state, where the current state has position and velocity. Okay, so this is what I mean. So in physical systems, if you have enough degrees of freedom, then you can relate what's going to happen in the future just to the present. But if you have access only to fewer variables, then you will by necessity have to know the past of those variables. So for example, the velocity can be written as the time derivative. If you discretize, right, time, you can say that the velocity is basically the position now and at a previous time divided by the time. So you can recast a model at least approximately, right, as a kind of delay differential equation, right, where you say you use the current information and some past time to predict the future. Right, so then that would give you this kind of appearance. So now in some arbitrary complex system, it could also be that really there is non-local time dependence, or it could just be that the variables you are using to model aren't enough. So therefore you need to have some past information. Right? Regardless, this kind of general description would hold. Right? But now since we're going to apply stochastic processes to physical problems, right, particularly for transport and so on, we will always be in a world where we can expand the number of variables to the physically relevant set, where we can predict things only based on what is the past current state, right? We don't have to know the history of the past. So such processes are called Markov processes. Okay? And what I want to do now is show how that simplifies this general fully complex picture. Okay? Because the ultimate idea will be that if I want to find trajectories, I can build up trajectories in terms of small steps, and for each step I just need to know the immediate past, right? So then I can step, and these steps are called Markov chains. So that's what we're going to do now. Yes. That is the interpretation of this conditional distribution, yes. Okay. So, sorry, just to help with maybe this will clarify things, what I should have also written here is to say this is the probability of the entire trajectory. So I should include yes. What should be before? No. No, it's after. This is the past, right? My notation is what is on the rightmost is earlier in time. So here I am saying I have the probability of all of trajectories that begin at y1, that begin at yn, come up to y1, then go to tn and go up to t1. Okay. Yes. The leftmost is the latest. Okay. So the way to understand this thing again is you imagine that I'm just looking at trajectories, okay, and there will be some fraction of trajectories that do this whole business. Okay. So I'm taking all that fraction and dividing by the fraction that executed the part of the past that I know or that I'm interested in. Okay. And that will give me this conditional probability, which is the probability of doing the future part given that I have done exactly this past. Right? So this basically tells you that there will be some trajectories, right, of all these trajectories, right? There will be some, the other way around. So of trajectories that did the past you're interested in, after that they will diverge from the future that you want. Okay. So it's not that just because I executed this past, I'm guaranteed to do this, right? Otherwise this would be one. So it's like these are all the trajectories, right? And from that I am accounting for dividing by those guys. So this is bigger, right? This is just the probability of doing only a part of the set. Then after that they will diverge. So this fraction is much bigger than this fraction, if you think of it in terms of fractions. Okay, any other questions? Okay, anyway, it will become clear as we go along. So now what I want to do is let's start to move towards Markov. So the simplest kind of way to simplify the history dependence, right, is to just say that it's completely independent. Let me get the name correctly. Yeah, completely independent. Okay, so completely independent processes are those where you can build up the trajectory just from this distribution PDF. Just remember I said this is like the simplest PDF. When someone says PDF, you usually think of this, right? Which is just saying, okay, that at some time I have a distribution of, so let's just say particles, right? But it's general. So if I'm thinking about particles, I say I have a system, at some time this is the distribution of particles. Okay, that's all. But imagine that I have such a simple system that it has absolutely, it's kind of, if you like, in terms of particles, it's mixing infinitely fast. It has absolutely no history dependence at all. Right? So if I drop particles, no matter where I drop them, instantaneously they are mixed. Right? And then, so if I look at the future time, again it is instantaneously mixed. So regardless of where I start a particle, its probability of being at some position just immediately relaxes to that. Okay, so it's like a, you can imagine a stirred tank or something which is mixing infinitely fast. The moment it hits, it's completely forgotten where you put it. Right? So the probability of finding it at some position is just this. And then at the next time, again, is just that. It has nothing to do with, where it was at all. So I can construct a trajectory just using this PDF. So this is usually the situation in games of chance, like tossing a coin. Right? So you can build up a trajectory of heads, tails, heads, tails, heads, tails by each time using a half, right? Because the process is completely independent of anything that happened before. But if you think of Brownian motion, certainly it cannot be like that, because where I am, the distribution of particles will depend on where I started, right? If I put all particles at the origin, then I'll have a certain distribution at a future time. Whereas if I start out uniform, I will obviously always be uniform. Okay? But imagine you do the same thing, you put a particle in a system, but where for some reason you have infinitely fast mixing, then you will have this kind of completely independent behavior. Okay, so to state it mathematically, it's saying that the probability of a trajectory is just the product of the individual probabilities. Okay, so, and this is how we do, remember when we get introduced to probability and we build up things like what is the probability of getting a heads and a tails and two heads, then we will just multiply the probabilities. Right? So that's like saying any particular trajectory, any realization of a sequence of events is just the probability of each of those individual events multiplied. That's because any individual event is completely independent. So games of chance and so on are usually like this, but not physical processes. And so in our transport course, this will not happen except in the kind of trivialized limit where we say infinitely fast mixing. Okay, but that's just the simplest case, and it also connects to the kind of probability problems you probably dealt with earlier. Okay, is this one clear? So now, only in this very, very limited case, you know everything about the system just in terms of this simple distribution PDF, instantaneous distribution PDF. Okay. It's only in this case. But again, in your introductory courses to probability, you're usually only given this, right? So if the heads and tails problem, this is half and half, because X is only discrete, right? Heads or tails. And then the probability distribution is independent of time, it is just half and half. You could have some other system where there is a time dependence, right? So for example, again, you take the coin problem, but you say the coin with each flip in time develops some bias. So that after some time, heads are 3/4 and tails are 1/4. Okay, but at initial time, it's half and half. So in that case, again, you would have this kind of complete independence. It's just that the probabilities of heads will start increasing in time because for whatever reason. Right? So you can imagine such systems, but they are still completely independent. So the time is, if you like, an explicit imposition of some change on the stochastic process. As opposed to the fact that trajectories will evolve in time just because they are going to different places, and the probability to go from here to here depends on what x2 is. So that is somehow like an internal intrinsic dependence. This time is the explicit dependence. So if you think about differential equations again, you have autonomous differential equations where the system is evolving, right? But there's no explicit time dependence. and then non-autonomous ones where explicitly you are changing something, like you're forcing or you're changing some parameter in time. Okay, so when you see this time, you think of it in this way, right? That it's like this explicit thing. Okay, so this is the simplest case, right? But most generally, more generally, and in fact in all physical processes, this is not enough. So let's leave this aside. These are too simple. We are not going to look at that limit. Then there are some other intermediate ones which we are not going to worry about now, but we'll go straight to Markov processes. Right, and these only depend on the present state or the most recent of the past. And the way I would write this down, right, is naturally in terms of the conditional probabilities. Is the simplest way to state it, because what we said here is the future states in principle depend on a trajectory in the past. Okay. But in a Markov process, this quantity can be simplified to only knowing this y1 and tau1, right? It doesn't matter what had happened before. So y2 can be anything. Provided y1 is the same, I will get the same conditional probability for the future. Right, that this thing is equal to now in between the x and t's, I may forget to put some commas. Okay. You forgive me, but you understand the pairing, right? So this is some state with a given trajectory, many more y's, but this thing will be the same as just retaining the most recent known past, which you can call the present, and then the entire future is determined by just the present. So this is the mathematical way to write what we mean, right? By saying that the future only depends on what's happening now. Right? What is the state of the system right now? Yes. Yes, so I was just thinking how I can reply to that. Okay, so see, what you're saying is correct, but it doesn't disqualify this statement. This is more general than what you are trying to say now. So in other words, let me say that what matters in the future only depends on where I am standing right now. Okay. So that means where I am standing now will determine what I do 1 second later and 2 seconds later. That's perfectly fine. It may be true that 2 seconds later depends on 1 second, but that doesn't mean it doesn't depend on this. Right? So what I'm trying to say here is I don't need to know all of this to determine the future. But this is still in the future. I'm not saying that I know this. Right? So what you're trying to say is, suppose I put the conditional distribution there. That's what we're coming to. So ultimately we'll be able to build it down into only one past and one future event and then make a chain. So right now I'm not saying I know this. Right? I'm just saying that I'm here right now. This is y1, tau1. Then there are various possible trajectories. The probability of any of these trajectories only requires me to know where I am now. I don't have to know my distant past. Now the question is, suppose I make one step, then I should be able to forget the y1 also. That's what we'll come to in a second. Okay, so what I'm doing now, it's important to pay attention because we are sequentially building to the chain. Right? In the end, if you want When you think Markov processes, you will ultimately immediately think the chain. But just to show you how the development is having step by step, let us go through this in this class, so that you will see cleanly that what I am assuming and how it is leading to the chain. So now from this, right, this is the only thing we are really stating when we say Markov. Now from this, using notions of conditional probability, etc., we can reach, I think, what the question was asking, right? Because what we can do is, we can now put in the condition thing here, using what we wrote here, right? So in other words, I can say that, okay, I'm interested in reaching x1. Now I can reach, and I've said that is the same as just knowing y1, reaching x1, I don't have to know anything before. Okay. But now this probability I can write as from y1 going through an x2 that I know, and then the probability of arriving at that x2. So this statement in fact implies something stronger. Because I can write so I will now say that I have come to x2, right, conditionally, and then use that. So I'm relating it in the following way. Given is that okay? So what I'm trying to do is relate the general conditional distribution to the conditional distribution of one step, which we can then call a transition probability. Okay, so I began with the general conditional distribution, knowing all the past to all the future that I'm interested in, and then said, because it's Markov, which is the only mathematical condition I'm applying when I say Markov, I can forget the distant past. And now I can use the fact, just a definition of conditional distributions, right, and their meaning, to break up the trajectory of the future into one step, the most recent step, or a sequence of steps, doesn't matter. So since we have only two things here, right now, so here I've written it for arbitrary steps, right, but let me just take the two case, then we'll generalize. So I just have two future steps. I can rewrite this as the most recent one, given that I am at x2. So assuming this past, times the probability of actually landing at that x2 just given y1. And now I can use the definition of the Markov process here, right, and forget the y1. Okay, and then you will see I'll have a chain. Given x2 t2 and y1 tau 1. Correct, exactly, yeah. And now I can use the Markov definition to forget the y1 tau 1, which has gone further in the past. Okay. And so finally what I am saying is that the future trajectory, right, the probability of the future trajectory going to x2 and x1 is the product of the individual transitions, right, from y1 tau 1 to x2, and then from x2 to x1. Right, and basically what I've done is this I can drop, right? Because it's Markov, I can drop that by one tower, okay? So what this last demonstration, if we generalize to an arbitrary number of intermediate steps, right? I can write the probability of any trajectory now. Right, so I take some trajectory, which is what I said, right? What we really need to know the full stochastic process is to know the probability of some trajectory, whichever intermediate steps you pick. But I can now write this as just the transitions, okay? Because what I did before is exactly this. I just labeled some of them as y's. And this can be now the conditional probabilities, right? And so on. Okay, so this is the probability of, let's say, my starting point. Okay. And then from there, I can go to x1 using the steps. Okay, and so each of these steps, these are like transition PDFs, if you like. The probability distribution of taking that particular transition. No, where did we assume that they are independent? No, that I gave you an example of trivial process. Now we are saying that is too simple, because that obviously will not hold for any general physical system that you are interested in. So I said that is the simplest version of having absolutely no time history or no time dependence. So now we have set that aside as being the very, very simple case, which we're going to go beyond that. And now we're going to say, if you like, the next simple, slightly more complicated, right, but still quite simple. So say that things only depend on the present or on your most recent past that you have access to. Okay. And then so that is a Markov process, not that they are independent, but only dependent on the most recent past or on the present, if you like. And using that fact, we just in the last two steps found that with that simplification, we can build the trajectory using only the transition probabilities, okay, or a Markov chain, the chain of events. Yes. Yeah, so you obviously, so the question is why this king came. So you have to know the probability of the starting point. If you like, that is your initial distribution where you put the particles at the initial point. Yeah, exactly. So you have, no, but why should it be fixed? I can toss a coin and start wherever I like. Depends on the system. So if we think of probability as a concentration or a fraction of the Brownian particles, it depends where I put them. I can put all my particles, so I can always start my experiments from a certain point. That's also okay. That just means this will be a Dirac delta. Or I can say I'm going to put a particle and let the experiment run at some position depending on some probability distribution. Okay, so then given I'm starting with this PDF, right, then given this, I take a step, and then given this, I take a step, and so on. So if you like, this is the initial condition somehow, and then I can construct the probability of any trajectory. Okay. So what we have done now is actually a huge simplification, because we started by saying I have some arbitrary stochastic process according to which I'm seeing all these trajectories capital X of t evolving in time. And then maybe for some particular reason I want to know what is the probability of seeing my particle at xn minus certain positions. Okay, and this seems to be extremely complicated, and I'd have to know all possible combinations of trajectories, right, somehow. And even, let's say I could observe the system, calculating such a trajectory directly from experiments seems almost impossible, because to get the probability, I would have to know the probability of all possible trajectories, which in experiment may never happen. Right? So let's say most of the trajectories will be very rare. right, in usual physical systems. So they have to do huge number of experiments or wait for an insane amount of time to be able to sample all possible thing and then calculate the probability. Right? So this is almost impossible to construct. But now we have made a huge simplification, right? Because now what we are saying is I don't need to do that. I just need to know what is the transition probability. So if I do a bunch of experiments and I see these transitions happening, right, then I can calculate the properties of the transitions and the properties of certain. So the same transitions will happen in many different experiments. Right? So I'll get a lot of data and then I can construct these transitions. And typically, one can make further simplifications on the fact that maybe the transition only depends on the distance between these points. Then that will again collapse things and make it much easier. Right? So you can already start seeing how in most actual physical systems, we will have some chain and then also a chain which is quite simple. Right? This is still general because I'm still assuming that the transition probabilities depend on x1 and x2. Okay, but usually it's something even simpler than that. It just depends on maybe the distance between these two states. So we'll come to those things. Yes. Sorry, yes, x1, t1. Thank you. Okay. Okay, so now that we have established this, what we would like to do is to get equations that help us determine these transition probabilities or to relate the transition probabilities to each other. And for that, we will use a probability balance. So this is now what we did in Einstein's derivation. Okay. So we'll try to get the Chapman-Kolmogorov equation similar to what Einstein got, right? Using for the Markov process, because remember that was the implicit assumption, right? We had said, or rather we said it explicitly, but not in this language. So we assume that the Brownian particle is undergoing some steps, delta, right? And this step doesn't depend on where it is now, right? It doesn't depend on the future. So what was that step? That step was just a transition probability, right, in this language. So we said, what is the probability of taking a step delta? Right? In this language, it's like saying, what is the probability of going from x2 to x1, where x2 minus x1 is delta. And then we had also assumed that that probability doesn't depend on x2. Right? So that all these probabilities are the same. I mean, they only depend on the distance. That's what I just said. Right? So Einstein had assumed that the transition probabilities only depend on the displacement delta, and so he could just specify the probability of delta. So that phi of delta, right, the probability of delta that we use in derivation, now you recognize is the transition probability of a certain step size. So then I can just sum up those things. Okay. And then we use that in this probability balance. But now we'll step back and do it in the general case. Okay. So what we'll start with is something similar to what he did, right? Is to say that the probability of, so I want to look at the distribution of states, right, at some time t1, and I want to relate this from the transition probabilities to some past time x2, t2. So this is the first step before I introduce transition. So what I'm trying to do here is build a relation between the probability now and the probability at the past. Okay, because what we're trying to do ultimately is to derive some kind of evolution equation for how this probability is evolving in time. And the only basic fundamental thing we have to do this is the balance of probability. So given that I have some probability distribution now, then the future time has to satisfy the consistency condition, if you like, that the sum of probability becomes 1. This is what we are doing. So at x1 t1, this probability must be the probability of coming to x1 t1 from x2 t2 when I integrate over all possible x2s. That's clear. So one can always do this, right? If I have some distribution, I can introduce a past state, and provided I integrate over all possible values of the past state, I will of course get the current distribution. Just remember, this is a trajectory probability. This is not a trajectory, right? This is just the current distribution. So the current distribution is like saying, what is the probability of coming to x1 from x2 and from some other x to some other x2, and then I sum up all those things. And now I can do the conditional thing. Right, given that I know that I was at x2 t2 and now times the probability of x2 t2. Okay, so I brought in the conditional probability. So you could go from here to there directly. It's quite intuitive, right? But this is just doing what I had done in the previous slide, the previous board, right? Where we said, okay, the trajectory can be broken up as into this conditional way. Okay, but this to this is also quite intuitive. Right? So I want to know what is my distribution at x1. That is given by coming to x1 from x2 and the probability of the distribution at x2, at t2, right? x2 t2. And I'm integrating over all those positions. Is that okay? Fine. So now what we're going to do is yeah, so now what we want to do is, this is still a relation for the distribution at this instantaneous distribution x1, but I want to introduce now the conditional probability even there, so that I can have a relationship between conditional probabilities. Okay? But so far I have not used any Markov thing, right? This is still always valid. Right? So to make sure the notation is right. Okay, so let's say I'm interested in this now. Okay, so why I introduced this is because I'm going to use this step here. Okay. So the take-home message from what this is always valid. Let me just write that. So always valid means it's not particular to the Markov assumption. So what I just showed you here is, if I have some PDF, I can always introduce a past time provided I integrate over that time. Right? So in terms of conditional distribution, if I have some PDF, I can introduce it as a conditional distribution on some earlier time x2 and integrate over that x2. So if I use the same logic now, but on starting with the conditional distribution, what I will do is introduce the intermediate time x2, just like we did a second ago. So this thing is the same as okay, that's like what I did here. So in fact, this is related to a question that someone asked a while ago, right? That I am saying that the y1 determines the entire future, right? But that's exactly the point here. So x3 does of course determine x1. This is the what I'm considering as given, right? But it can determine x1 through many intermediate steps, of course, right? Provided I integrate over all those steps, I'll reach the probability of getting x1 from x3. But now again I can use the conditional distribution here. And now I can use the Markov fact, right, and drop the x3. So this is also always valid. Okay. But now for Markov processes, right, this will become let me just rewrite the original thing here. Okay, so this is the Chapman-Kolmogorov equation. Okay, so once again, this is what we said basically in Einstein's equation, right? We wrote the probability of coming to x1 t1. We had suppressed given this, but basically we had written assuming that I am at the origin at the initial time. Right? What is the probability of being at x1 t1? And that was written as the integral of being at some x2 t2 given my initial condition times the transition probability, which was the PDF of delta. Okay, so if you go back to your right earlier derivation, we would, what Einstein did was the probability of x and t, this given xt33, let's say, is the initial condition, right? So that was suppressed. We implicitly said I'm starting all the particles at some initial condition. So the probability of coming to x1 t1 at the future time t1 was written as the integral of taking a transition step, right, such that I come to x1 into the probability of being at the x2, which brings me to the x1. Right? So this x2 was written as x minus delta into the probability of delta. Okay, so that's why we said that what he wrote down was essentially the Chapman-Kolmogorov. Now we are seeing it in the general case. And finally it's quite intuitive, right? Once we understand that, which is again quite intuitive, the idea of the Markov chain, that I can reach the future state through steps, each of which have their own independent transition probabilities. Okay? So what I'm saying is I can come from x3 to x1 by stepping through x2, and if I integrate over all those possible x2s, I will get this transition probability. Okay? So I can use this now in many different ways, right, and we will do that in our derivation. So I can think of this as going from some initial condition up to the future time of interest, and the fact is that I can do that by taking some intermediate steps or intermediate step, provided I integrate over all those possible intermediate steps. The other way of thinking about it is I can construct transition probabilities in terms of substeps. So let's say I want to know this transition jump. I can find it out if I know the substep transition, okay, just by doing the integration. Yeah, so all we are saying is just balancing the probability, accounting for all the paths, and using the Markov fact that I just need to know the previous time. So the only place I have used Markov is here. That's what I want to point out, right? So Chapman-Kolmogorov just comes from a probability balance. This is completely general. This is also general. The only big simplification is when I forget this past in the trajectory. Okay. Now, why this is nice is this will now bring us towards stochastic differential equations or continuously evolving systems. Because if this is true, right, then simplification will arise if I make very, very small steps, because then I can think of obtaining some kind of differential equation for the evolution. This is also an evolution equation, right? It's telling me that, let's say I know P x3, T3, I want to find this conditional distribution, because then I can step forward, right? That's what this is telling. So given the initial condition, I can step forward and get the probability of any trajectory, but I need the conditional guys. And the conditional guys have to satisfy this balance. So what is now tempting is to think that what if this T1, T2, T3 are arbitrarily closed, right? They're all small, small steps. Then is it possible for me to use this kind of probability balance to arrive at a differential equation for the evolution of the probability, right? So provided I specify what is the infinitesimal transition, because then I can build it up just as a sequence of steps. That's what we do in a differential equation, right? When we say dx dt is equal to f of x, we are just specifying what is the instantaneous rate of change of x, or what is the small change in arbitrary small time. And usually this is something that becomes simple to specify, physically speaking. So again, if you think about Newton's insight, his insight was that specifying the velocity of some object, the position of some object, of course, I cannot do, depends on the system. Specifying even the velocity seems to be not possible, but there are simple, general, universal expressions for the second derivative of the velocity, right, which he called force. Okay, so that an arbitrary number of systems, planets doing all kinds of weird, so what people were doing earlier, specifying the position, right? So different elliptical orbits and Ptolemy cycles and whatnot. We were directly trying to find some coherence for the positions of the planets, for their orbits, that is for x. Right? But that was a hard thing to do. Right? Even for a limited system like just the planetary motions, we got all kinds of complicated structures. But what Newton said is, if I look at the second derivative of these things, right, then everything becomes the same. It's all inverse square law. So the idea was again to introduce this notion of the differential change. That is what was simple, right? Any finite change quickly became complicated because it depended on where you were in space and how you were evolving. So the same thing will become simple here, because often we will be able to specify these differential transitions, because that depends on forces and so on. Right? So that's why what we will be doing in the rest of the course is using Chapman-Kolmogorov, but applying it to small changes. Right? And the way we will do that is we will use this to derive a differential equation for the evolution of the probability, transition probability P, and we will find that that basically gives us this advection diffusion equation, like the type that Einstein derived. So this is essentially the program of the next couple of lectures or so. But to do that, the key idea now, if I want to take differential steps, is I have to work with processes that are continuous in time. Okay, so if our program is to try to apply Chapman-Kolmogorov to very, very small transitions, small time steps, and to try to get a differential equation, I can only do this if somehow my process is continuous in time. So it's a stochastic process that doesn't take big jumps, right, and which can be described as a smooth trajectory. So this is different from saying that x can take all values. These are two separate things. Okay, so a nice example that is again in Gardner's book, and by the way, this whole thing is following Gardner. Okay, so if you have the book, you can look at it again. Yes, so what I was saying is, you think about ideal gas, right, where there are gas or billiard balls, right, which are bouncing around in a stochastic kind of way. Right? Now, if you think about this system, you have, let's look at the velocities of two billiard balls which are bouncing around. Now, the velocity can take any in the continuum of values, right? So if you think of velocity as x, x can be anywhere on the number line, or it can be anywhere in space. So the variable x is got continuous support, right? It can take any values. It's not that the velocity can take only discrete values. But however, will the velocity change continuously in time? Right? So for the hard sphere collision problem, it won't, because they'll come and they'll bounce. So if the velocity here is something, it reverses, right, across an arbitrary small time. So even though the velocity can take smooth values, its evolution in time is not smooth, right? It's not continuous. But the position of these balls is continuous. Okay, so they are moving slowly, they come here and then they'll move. They'll not teleport. Okay, so the position of those billiard balls will be a continuous process and described by continuous Markov process. That's the case in Brownian motion, that the position does that. But the velocity will not be describable as a continuous Markov process. Okay. So, but we are thinking now about the continuous processes, and these are such that one way to think about it, the more intuitive way, is that the trajectories I drew up on top, right? So you have this trajectory that is moving around, okay? It may be fluctuating and so on, but it's continuous in the sense that there are no jumps. So how do you define a continuous function? So if you remember, the idea is of it being close to each other is if I have to go from one point A to one point B, I can go from A to B only by going through all the intermediate positions, right? So if you think about it as x having only one value, right? If I have to go from this value to that, I have to go through all the values in between. I cannot take an arbitrary jump. Okay. In terms of epsilon delta kind of thing, the idea is if I'm evolving in time, for any given value of epsilon, no matter how small, I can shrink the time difference to go below that epsilon, right? So I can always, at some time close enough, I will be arbitrarily close to my starting point. So this is something that's evolving continuously. Now, how do we know that if I have a system that is governed by these transition probabilities, that I will satisfy this condition? In other words, let's say I have this kind of Markov process, and I'm going from xn to n minus 1 and so on, right, up to n1. These will be jumps because the t's are big. But if the t differences are made small, can I be sure that these x's will become arbitrarily close to each other? That's the question. If that is true, then my trajectories will become continuous in time. Okay? And then I can think of getting a differential equation for the trajectory capital X. Right? Or I can think of getting a differential evolution equation for P itself, because the P here, let's say here, right? If I want to get a differential equation for this P, right? If T1 is close to T3 and I want to do dP dt, then this P should evolve continuously in time, otherwise I cannot do that. Okay, so I'll just write down the condition here and we will use it in subsequent lectures when we derive the Fokker-Planck equation. So the idea is, let's say I'm making a small step in time. So I'm thinking about the probability, okay, of taking a step from z to x, okay, for a small change in time. Okay, so let's say I'm starting at some z. What is the probability of taking a step from z to x, okay, when the time difference is small? And I'm interested in, is there a probability of taking big jumps, right? So I'll do this integral only such that epsilon. So this is where my epsilon comes in, right? When we're talking about not taking big jumps. Okay, and the condition says that the limit, this probability in the limit delta t tending to 0, and there's a 1 by delta t sitting here, right, that this thing should be 0. In other words, so if I say it intuitively, the probability of that's the intuitive condition. Okay, so the idea is if I have some stochastic process with a transition probability that is defined, right, if this transition probability is such that my chance of taking big steps, right, where big means greater than epsilon, and I can vary epsilon as much, so I can make epsilon, right, small if I want, right, but the probability of taking this finite step as my time shrinks to 0, right, as the transition time shrinks to 0, that should decay faster than delta t to the 1, like let's say delta t square. Okay. So that's just setting the bound on how high that probability can be. So provided the probability of taking a big step falls faster than delta t, then my trajectories capital X of t will be smooth. Another way of stating this is, it's like saying if this probability divided by delta t is a rate, right? So we think of probability as a fraction of all the conditions I'm doing experiments on having some jump bigger than epsilon. So this is the number of jumps. If I divide by delta t, that's a rate. So it's the rate of taking big jumps. That should be 0. This is what this guy is saying. Okay. Now the important thing is that we will use this condition when we derive this Fokker-Planck equation in the next class. Okay. So even it goes back to what Einstein had done loosely when he wrote down this Chapman-Kolmogorov for his problem, right? So remember, this was the probability of taking steps delta, and this was p of x minus delta, right? And then he did a Taylor expansion, right? He Taylor expanded x2 about delta and so on, right? So that's when I had said, okay, we are doing Taylor expansion. We are assuming that the tau is small enough that we can do this, and we are assuming that my steps delta are small in some way so that I can expand x minus delta about x. Remember? Otherwise, we cannot do Taylor series in space, right? Unless I say my steps are small. But I was taking a transition probability without specifying anything about it. Okay, so this is the formal thing we will be using. Right? So to be able to derive a kind of differential evolution equation or a diffusion equation for the probability distribution, we need that transition probability to be such that big steps are not possible. Right? Otherwise, these discontinuous transitions will happen. And we will see that provided we require our process to follow this, which is what we need for continuous processes, we can justify the Taylor series type development in Einstein's derivation. So the important physical idea to keep in mind is the condition that one needs for this stochastic trajectory to be continuous is what one needs to do a Taylor series kind of expansion and derive the diffusion equation, which is what Einstein didn't say explicitly, but that's what we will use. Now, how exactly this condition is derived, it's useful to look at. I will not do it in the course for interest of time, but if you want, you can read more about the Lindbergh condition. Again, it has interesting connections to the central limit theorem and so on. But we'll just take it as a given. The intuition is what I was trying to say here, right? That it's basically bounding what is the probability of taking big jumps, okay? And that should decay in time as you take the interval delta t to 0. Okay, so is there an obvious example that we already know of such a continuous process? So I'm saying Brownian motion is one such process. Okay? And that's the assumption, otherwise we would not get the diffusion equation. Okay? So now let's assume that Einstein's derivation was correct. Okay? After all, he got the correct root mean square diffusion and so on. And then this p, right, or this p, this transition probability is governed by the diffusion equation, right, that Einstein derived. Then what that means is we can get from the diffusion equation, we can get the transition probability by putting z comma t as the initial condition and finding what is the probability at some future time t plus delta t. In other words, solving the diffusion equation with the initial condition that the particle was at z comma t. Okay, so remember, we already got a solution. If you look back to your notes, I said if we start the particle at origin at t equal to 0, the probability at the future time is a Gaussian, right, with a variance that expands with time. Okay, or as the time interval will go to 0, the variance will shrink. Okay. So when you apply it here, you will see that the transition probability for a Brownian particle, okay, for the Brownian process, is a Gaussian. Right. Instead of the Gaussian being centered at 0, the Gaussian will be centered at position z. Okay. And to be a Gaussian, and the width of the Gaussian will shrink as this delta t goes to 0. Okay. And what am I doing here? I am integrating the Gaussian only outside a distance epsilon, right? So if you want, if z is at the origin, right, then there is a Gaussian, and I am integrating the function only outside a distance epsilon from the center. So you can see whatever epsilon I choose, if I shrink time, the Gaussian will shrink within the epsilon, right? And its tails will decay very fast. So the question is, the Gaussian tails, do they decay fast enough such that what I'm integrating outside is less than delta t to the power 1? And the answer is yes, you can verify it. It's because the Gaussian decays extremely fast. So that Brownian process, if the Brownian process was described by that diffusion equation that Einstein derived, it would satisfy this condition. Okay. Yeah, it's like the same the way it's done in usual continuous function calculus, right? So there what we say is, okay, whatever epsilon you choose, however small, if I shrink delta t sufficiently, I will come below that epsilon in terms of the difference the function undergoes. So, but this is a similar kind of thing, but now because we are dealing in probability, we say that if this integrates to 0, so the precise statement is if this integrates to 0, the probability of having a finite jump is 0, right? Or with probability 1, you will have a continuous trajectory. But where we will use this is when we do the derivation of the Fokker-Planck equation. So we will now do it in the forward way, which will automatically justify. So we'll use the fact that it's a continuous process to derive the diffusion equation for the PDF. What Einstein did is sort of just directly reach it, but we can show that whatever answer he got is consistent with it being continuous at this point. Then in the next class, we'll directly use this condition. Okay, so I know that what we did today was a bit abstract, okay, and in some places may seem like overkill because in the end the final answer is kind of obvious. If this is obvious to you, that's perfectly fine. For this course, that intuition is what we need, right? And then we will move on to other things. But I thought it's useful once to just see the thing so that you have the steps at least roughly in mind. You can always come back to this. Okay, so just to refresh, it's good to see in the general perspective, right, that stochastic process does not mean that they have to only depend on the past and you will always have this Markov chain. And in general, you have the general picture. And when you think of stochastic process now, don't only think about that simple PDF, which is just a distribution at any instant. Right? Rather, when you think stochastic process, it means I really need, every trajectory of the system, its entire history is associated with a probability or a probability density. So there's a probability density on the trajectories. Right? That is the full scope of a general stochastic process, okay? Which is much more complicated than when we think of just a system evolving by differential equations, right, or a dynamic system. So you have a probability associated with every trajectory. However, if we now say that the system only depends on its most recent past, then it dramatically simplifies because we don't need to now know the probabilities of all possible trajectories. We just need to know transition probability. Right? So given an x1 and an x2 at time t1 and t2, what is the transition probability? So this is already a big simplification. Okay? And this is true for any process, whether it is continuous or not. Right? So if it is a discrete process, so it's evolving in discrete jumps. Okay? So that I can actually go only from x1 to x3 in some big steps, right? I can still use this Markov chain idea. So for example, when you have chemical reactions and so on, so that you have finite number of molecules interchanging, right? Then you have to treat it discretely and you get things like master equation and Gillespie simulations and so on. We will not go that route because we are interested here in mass transport where we will look at continuous processes, okay? But these things of course can be related, we can discuss them more. But now we are going to focus even more on just continuous processes where the stochastic variable of interest changes continuously. And then we will see that we of course have to, that implies the following condition on the transition probability. And we can now build up trajectories using these infinitesimal transition probabilities, right? Or in other words, we can have a differential equation for the conditional probability that we can ultimately use to say, okay, given that I start with some initial distribution, right, I can evolve the system forward in time because I know the transition probability as a differential equation. All right, any questions? So the plan for the next class is we will now focus on systems with transition probability satisfying this criteria, okay, and apply the Chapman-Kolmogorov and try to see if we can use Taylor series type development, right, just like Einstein did. So remember, the idea is basically what if x2 is close to x1, right? Then can I use a Taylor series to write the probability of x1 in terms of derivatives of the probability at x1, right? So I can deal with x2. Similarly, what if t2 is close to t1? Then can I use time derivative on the p, okay, and then develop this something like a differential equation. Okay, so thank you.